Hello, everyone. Sorry it's been a while, but it's been um, test season, so review has been scattered. So today we're looking over problem set 14, so a little past the previous ones we've done, and we're talking about Lewis structures still, but with resonance, delocalization, expanding the octet, and bond order, and what those all kind of mean. Hopefully, this will help to explain. So first, let's talk about resonance and delocalization. So first, remember that for that nature wants to be stable. This is all about stability. So resonance isn't real. All it is bookkeeping. It's bookkeeping for the electron is. So here we say it could be here, the electron could be there, or it could be here. And that's resonance, and these are our resonance structures. But in reality, it's the electron is delocalized or delocalization, which means it's just being like spread all over the atom. So like this charge is being spread all over. So or here it's being spread all over. So that's what like delocalization means. It's spreading the charge all over the atom. And that would make it more stable. So really, delocalization is like the mix in between these two. And so we see like, well, it could be there, it could be here. So maybe it's like this little mix of like spreading the charge between these two places or something like that. Okay. Now let's talk about formal charge. Okay, so how you find formal charge is if I have an atom, I'll take O, and I have, say, two oxygens there, and then a bond over there, and then a bond over there. That's not geometrically happy, but that's fine. So this has an octet. It has 1, 2, 3, 4, 5, 6, 7, 8. Haha. It has an octet. But how we find the formal charge is by, just think about it as subtracting its valence electrons. So you take its valence electrons and subtract the things that are around it. So oxygen has a valence of 6, and there's 2 electrons here, 1, 2, but then there's a bond here, and a bond there. So that's 1, 2, 3, 4, 5. So 6 minus 5 equals 1. So this has a plus 1 charge. So that's how you find formal charge. And the pattern, continues for all others. But what does it mean, and why does it matter? And it turns out that in drawing a Lewis structure, that when you have a formal charge will take precedence over filling an octet. I'll show an example of that in just a second when we talk about expanding the octet. But formal charge is all about the molecule finding stability. And so you want the smallest numbers of formal charge. So you don't want like 2s or 3s or something like that. You just want 1s, or as small as you can get them, really. So you could have 2s or 3s, just as small as you can get them. And if you have a negative charge, like a -1, you want it with the most electronegative atom. So that would be like a fluorine, an oxygen, nitrogen, more over to the right side of the periodic table. Okay. So that's formal charge. Now, expanding the octet, this says we have this octet rule that says that you need 8 electrons around. But sometimes a atom will break the octet rule, which also means it could break it by not having an octet. And we will see that in this example here, where we have bromine trifluoride, and it's bonded to where fluorine has an octet on all 3, but bromine only has 6 electrons around it. Boron only has 6 electrons around it. But if you take the formal charge, you find that all of these have a formal charge of 0. So now we need to, so now we see that this is how the atom is formed. So otherwise it would have had 3 resonance structures, but this is how it's formed because of the formal charge, and the formal charge takes precedence over the octet rule. So when you're making something with like xenon, where it's definitely going to break the octet rule because xenon already has 8 valence electrons, then you want to look at what structure is going to give me the least amount of formal charge. And if there's multiple, that's when you draw resonance structures. If there's multiple structures that have the same amount of formal charge. Okay, last thing, bond order. Bond order, what you do is you take bonds divided by the positions to bond, or possible positions there are to bond. Something to note though, this is between two atoms, okay? So usually see, what's the bond order between O and O, or O and C, or C and H, or something like that. So you tell the bond order between those two things. So for example, if I had carbon dioxide, which I think looks like C and then a double bond O like this, and it'd say, what is this CO bond? So even though there's two bonds of OCO, then we just need to look at one side. So we'll look at this side. And so we take the number of bonds here, that's 2, and we divide it by the positions to bond. How many positions are in the bond? And so basically what is the side between them? That's 1. And so this has a bond order of 2. Bond order decides the strength of a bond and also the length in between it. The stronger the bond, the shorter it is, because as you can imagine, you know, a buff guy is pulling you closer in it, or they're strong, they're pulling each other closer, so the distance is shorter. So just remember that it's the amount of bonds divided by the position of bonds. If we had a resonance structure, I'm just gonna do atom X and say there's 2 here, 1 here, 1 here. And it's gonna, well, I'm gonna say Z and atom Z and atom X. Sorry, my handwriting's bad. And now it's gonna ask me what's the bond order between these. And so since this is like a resonance structure, and these can be drawn, and I'm pretending like this is a resonance structure, so this can be drawn in 3 different ways. Now you take all of them in possible bonding positions when you're figuring this out. So you say, okay, how many bonds are there? There's 1, 2, 3, 4 bonds. And how many bonding positions are there? There's 3. And so this is going to be a 1.333, so on. Bond order, BO. BO, because it smells bad. So that's kind of bond order. And again, it tells the strength. Okay, hopefully this helped.